Good morning to all participants. Thanks for participating continuously in our program, and today being the last program of our 2022. On the today's subject is electrical safety audits. So we already concluded, or we already made the part one of this electrical safety audit, and today we are going to discuss about the part two. In the part one, without much introduction, let me go to the subject straight away. In the part one, okay, before that, a small subject which I wanted to explain you is this. Last time also we explained. We have registered a society, National Federation of Engineers for Electrical Safety. Now all the training programs we are planning to conduct under the name of National Federation of Engineers. Not only training programs, we are also coming out with some kind of accreditation system which will answer the ever unanswered question: who is an electrical auditor, or who is an electrical designer? So our system, we are trying to make an accreditation system from the Quality Council of India, or National Accreditation Board for Certifying Bodies, NABCB. So NFE probably will be an NABCB accredited body who can authorize, or who can accreditate professionals, electrical engineering professionals, based on ISO 17024 standard. So this work is going on. Probably we will make an announcement in next few days. So we request all electrical engineers to join this professional forum. We can improve the safety situation in our country. So in the first part of our program, we discussed about safety audits and verification. Safety audits and verification. Just a moment. So I'm showing you on the screen the definition of audit and verification. Audit is a systematic, independent, documented process for obtaining records, statement of facts, or other relevant information and assessing them objectively to determine the extent to which specified requirements are fulfilled. On the other side, the definition of verification is confirmation through the provision of objective evidence. Please note the word objective evidence, very important. Confirmation through the provision of objective evidence that specified requirements have been fulfilled. The term verified is used to designate the corresponding status. Design verification is the application of tests and appraisals to assess conformity of a design to the specified requirement. So if you look at the definition of audit and verification, actually audit is not applicable to a subject which is a safety, or it is not applicable to a subject where objective evidences are required for the confirmation of certain objective. So verification is the correct word. Now, where you can see this differences are very interesting. You can go to, I'm just opening the Electropedia. Electropedia is nothing but the international IEC's, International Electrotechnical Commission's vocabulary. It is actually the IEC 610050 standard. Here I have opened the Electropedia. I am typing audit. So here you will see the wording of audit. You see, systematic, independent, documented. Let me zoom it more. Systematic, independent, documented process for obtaining records. So I will also show you the meaning of verification. Confirmation through the provision of objective evidence that specified requirements have been fulfilled. All of you can note down this particular website called as Electropedia, or International Electrotechnical Commission's vocabulary. You can also go to ISO online browsing platform. ISO International Standards Organization online browsing platform. And if you have any doubt about a specific term, you can you can search the meaning of the term in this platform. So this is a very good platform by IEC. Now coming back to our presentation. Verification is the correct word which has to be used for our purpose. This means audit is not the correct term to call. In the last presentation, we discussed about the inspection and testing. There are 18 inspection points, and in the last presentation, we discussed about the first inspection point, which is method of protection against electric shock. Method of protection against electric shock. There are several methods. There are several protective measures applicable for basic protection. You can see here on the left side, basic protection plus fault protection. Both are necessary in an electrical installation. Basic protective measures include insulation of live parts, barriers or enclosures, obstacles, and placing out of reach. Say, for example, barriers or enclosure. A live bus bar is inside a panel board. It is inside an enclosure. It is a classic example of a basic protection. But once when you put a live part inside an enclosure, there are several safety measures which you are supposed to carry out in the enclosure. Don't think that by putting a live part inside an enclosure, you are achieving safety. It is not like that. There are several rules which we are supposed to follow. Similarly, fault protection against, earlier we call it as indirect contact. In new standards or new name is fault protection. Several protective measures are there, such as automatic disconnection, extra low voltage, separation, double insulation, and so on. Today, we are going to discuss about the protective measure for fault protection called as automatic disconnection. So please note that we are going to discuss one of the several protective measure which can be applied or applicable in an installation. By making only this particular test, don't expect that your electrical installation is safe. So please make a note of it. Also, protective measures like there are protective measures which offer both basic and fault protection, enhanced protective measure. So this is the general idea of fault protection or protection against electric shock. This is not about fire or safety of equipment. This is only about shock protection. Now, there are 18 inspection points. The first inspection point is the kind of measure which is implemented, shock protective measure which is implemented in an installation. Followed by that, there are 10 tests included in the standard, but I have put 11 tests because the last one is sometimes very much important for India, which is called as a PAT, Portable Appliance Test. So probably in future standards, you will be able to find these 11 tests. Of course, this is also included in the upcoming National Electrical Code. So today's discussion is specifically about effectiveness of automatic disconnection of supply. We are going to discuss only the first part. On the day one, last time, we discussed about the resistance measurement of conductors. Of course, we only discussed the important points of resistance of conductor. We didn't discuss how the test is carried out. Today, we will discuss about the protective measure serial number 6 in IS 732 or IEC 60364, or let's say people from outside India, you can refer BS 7671, the test number 6, effectiveness of automatic disconnection of supply. So the importance of it and how it is carried out and why it has to be carried out is or the basic understanding of automatic disconnection of supply. Now, for automatically disconnecting a supply, you need a protective device. The protective devices, one moment, please. These protective devices, The first category of protective device is called as OCPD, overcurrent protective device. In an overcurrent protective device, the overcurrent and the disconnection time, while selecting an OCPD in a particular circuit, we have to be very careful. We have to find out the overcurrent versus disconnection time requirement, and we have to select the protective device appropriately. And always you should keep in mind that every OCPD, there is a conventional disconnection time and the conventional disconnection current. This means a current of up to 1.45 times its rated current, the device can take up to 1 hour to trip. Today's devices are faster. Probably it may offer much faster disconnection, but the circuit has to be designed in such a way that up to this much time, your circuit shall withstand that overcurrent, or the device which is having an overcurrent must be able to withstand this much time and this much current. These devices can be used for overload, short circuit, and earth fault in TN system. Earth fault in TN system. Please note that the effectiveness of automatic disconnection of supply as a fault protective measure means against earth fault. We are talking about the last one, earth fault in TN system. You can have a OCPD for disconnection. Similarly, we have one more protective device which can be used for automatic disconnection of supply during earth fault or earth leakage. This is called as RCD, residual current device. In residual current device, for example, 30 milliampere is the maximum allowed shock protection. The residual current for a dry area for 50 Hertz AC is 30 milliampere. Of course, DC, pure DC, say for example, pure DC, the RCDs are not yet available in the market. Still, it's under development. Of course, the current perception is 80 milliampere. It's not 30. So basically, RCD is a device. 30 milliampere RCD is for shock protection in dry areas. Please note, dry areas is also very important, not for wet areas. And 300 milliampere is for fire protection. Leakages from equipment can ignite fire. An RCD of up to 300, maximum 300 milliampere residual current can protect your installation from fire. So this residual current, in simple way, you can think that it is the current escaping from the circuit. In the sense, in a three-phase circuit, the sum of the current is 0. In a single-phase circuit, the current going to the equipment and returning back, the sum must be 0. If there is a current which is escaping from the circuit, then the circuit, I have a picture, I will show you later. OCPD, please keep in mind, there are 3 types of OCPDs available, B, C, D, MCBs, for example. MCB is a type of OCPD, and MCBs are of 3 types, B, C, and D. The difference of these devices are basically in the quick disconnection time. Quick disconnection time means instantaneous tripping time. A B type MCB require up to 5 times, or anything above 5 times the rated current, it will disconnect in 0.1 second. C type 0.1 second means it need 10 times the current, and type D 20 times the current. So we discussed this subject as well in the last explanation or last part of the webinar. Our problem which we face in the market is type B MCB here. Type B MCB with the 5 times disconnection current is actually required to protect the final circuits in example in a residential building, or let's say in a hospital where multiple devices are used or something like that. Now, these type B MCBs are generally not available in the market. You cannot buy it across the counter. If you go to a shop and ask for a type B MCB, they will say, I need 1 week for arranging the material. I need 2 weeks for arranging the material, which is actually not good. As a result of non-availability of the material, we always use type C MCB. Please note that fault protection by a type C MCB, shock protection by a type C MCB is a little bit difficult than a type B MCB in a TN system. Now, I'm showing you a TN system. TN system consists of, on the left side, you can see a transformer. On the right side, you can see, say, for example, an equipment, and then there is an OCPD, there is a protective device, there is an OCPD, and what is important is the green wire, which is nothing but the fault return path, metallic fault return path. Metallic fault return path in the sense, in case of a fault, the fault current from the equipment is returning back to the source through the metallic fault return path. This metallic fault return path resistance probably is, let's say, 100 milliohm or sometime even 2, 3, 5, 10 milliohm in a very large installation, or sometime in a very residential kind of situation. Probably the for metallic fault return path is, let's say, 300 milliohm, 500 milliohm, things like that. It is very, very less. And the impedance of this particular circuit or this loop, please note that the fault current is now circulating in this particular loop. The impedance of this loop decide the amount of the current, and this amount of the current decide the disconnection time. For a fault of negligible impedance, see here on the right side, I have put a kind of a fault, the symbol for a fault or symbol for a faulty device. Now, the impedance of the fault decide a major factor, which is the disconnection time. The touch voltage is decided by the impedance of the fault. Now, in case of a fault of negligible impedance, a lot of current should flow in this particular loop. As a result, the impedance of the circuit is influencing the fault current. I have put IAC, but actually it's a fault current. The disconnection time or the disconnection current is decided by the impedance of this loop, and the fault current is decide the disconnection time. And in the standards IS 3043, IS 732, or National Electrical Code and all, this formula is very much explained. You can also refer those standards to have a better idea. Most of the time, our electrical installation is of this type. There is no metallic fault return path exists. We call it as TT system. Source is earthed separately. Then, one moment. Source is connected to earth electrode. Equipment or the installation is connected to a separate earth electrode. Please note that in order to achieve a TT network, both these earth electrodes shall be electrically independent. Independent in the sense, these two must be at certain distance, so that in case of a fault current flow through one of the electrode, there is a voltage gradient created, and the voltage gradient shall not influence the other one. So electrically independent earth electrode. This kind of a network is called as a TT network. The technique which is explained in the previous slide, fault loop impedance and disconnection by an OCPD, technically will not work in this particular case. In this particular case. Now, for disconnection, what we require is a different technique. See, in this particular case, the fault current is flowing through the earth electrode, through the soil, through the earth electrode of the source, and it is returning, and now the fault current is flowing through this particular loop. The problem in this particular case is the fault loop impedance will be very high, of the order of few ohms. Say, for example, 1 ohm, 2 ohm, 3 ohm, not actually, it's always more than 2 ohm, maybe 10 ohm, 15 ohm, like that. OCPD is not at all efficient in this particular case. And you always require a device called as RCD, residual current device. So if you go for this kind of a network, which is called as a TT network, fault loop impedance will be very high. Automatic disconnection by OCPD will not happen, and you require an RCD, a device called RCD, residual current device. When you select RCD, please note that there are 4 types of RCDs. Depending upon your usage, you should select the appropriate type of RCD. Say, for example, for usage is completely sinusoidal. That means there is no semiconductor devices. You can use a type AC. Any of these 4 type of RCBs can be used. There are 4 types: type AC, type A, type F, and type B. All the 4 can be used. If you have pulsating DC load, such as power supplies of computers, power supplies of television, and nowadays all these modern electronic devices, then the chance of leakage in the pulsating DC also can create a shock. And for that particular purpose, you have to use a type A RCD. Similarly, for high frequency, let's say, for example, single phase inverter application, you need to have a type F RCD. Similarly, for a smooth DC, say inverter, 3-phase inverter, or inverter in the sense this is variable frequency drive 3-phase, or a solar PV installation, under such condition, solar PV without simple separation, under such condition, you need to have a type B RCD. So 4 types are there. You have to select the RCD appropriate to your application. Please note that all these RCDs are AC duty, in the sense these are for AC application. The smooth DC is a leakage, a DC leakage in an AC line. Don't think that this type B RCB is for a DC purpose. It is not like that. It is for AC purpose, but the leakage is DC. Now, earlier days, we were using a device called ELCB, earth leakage circuit breaker. Nowadays, these circuit breakers are not much available in the market. I think it is not at all available in the market nowadays. But it is interesting to understand the method of operation of this particular device, because we are talking about automatic disconnection, how to ensure that your device is tripping and how to get shock protection by this protective measure. Now I am showing you a TT network. There is a fault, and the fault current is going through the earth electrode, and now probably it is circulating in this current. Now ELCB is a device which measure the current which is flowing through this circuit, through this earth wire or this protective conductor. So there is a conductor which is carrying the leakage current, and the leakage current is measured, and a mechanical device is connected which will disconnect in case of a leakage current more than its tolerable or more than its set current, say for example 30 milliampere. So ELCB works by the principle of measuring the leakage current through a wire or current through a wire. Now this device disconnect in case of a current higher than 30 milliampere, and your installation will become safe. ELCBs are very critical while doing earthing. For example, in your installation or in your equipment, if you have one more earth leakage part, then you cannot achieve safety in this particular case, because the ELCB is measuring current only through one wire, but you have 2 wires which is connected. As a result, ELCB will not be efficient. ELCB, very important to understand that this particular route where I am showing the cursor, the earth return path, as well as the earth electrode, both must be 100% proper. If there is a loose contact in this wire, or if there is no earth electrode, under these conditions, ELCB will not work properly. So both the route of the earth leakage path and the earth electrode are important for an ELCB to work. ELCBs need proper routing of earth wire and earth electrode. Any mistake or non-connection of earthing will lead to shock hazard. ELCBs cannot be used as a protective measure against direct contact. Nowadays, ELCBs are not much available in the market, especially in India. I don't know about other countries. Nowadays, we use a device called a residual current device, RCD. RCD works in another principle. Here, some of the current is measured, and residual current, you can, for a layman, you can think that it is a current which is escaping from the circuit. So, a residual current, in case since we are measuring some of the current, in case of any leakage through a different route, that particular current is measured with this mechanism, and it is disconnecting the circuit. Automatically, it is disconnecting the circuit. As a result, safety is achieved. Now, what you should understand in this particular case is, in an RCD, even if there is no earth wire, let us say by mistake, there is no earth connection, you have an equipment and this earth, the protective earth conductor and the earth electrode itself is missing. You have a good RCD and there is a fault, the device will not trip in normal condition. But as soon as somebody touches the body of this equipment, then this device will trip. As a result, the person is safe against shock. Of course, he will get a small shock, but that shock is not stronger enough to create a big problem. Now, the purpose of this earthing and the earth electrode in case of an RCD is, before somebody comes and touches this particular equipment, that means as soon as there is a leakage, your device should trip and keep the installation safer. No, it means that by making this earthing connection, protective connection, you are protecting the person. So an installation without earth, but with an RCD, person may get a shock, still safe, and RCD trips. Very important. So please note that ELCB, the mechanism is a little bit different. RCD, the mechanism is a little bit different. Now, once when we go for a TT network, we have to understand this particular mechanism. How? Because our idea is to understand how automatic disconnection works and how the earth electrode, what the importance of earth electrode in case of a TT network. Without understanding the method of working of earth electrode, sometime we will end up with trouble. I am trying to explain you what is the earth electrode and how it has to work in a low voltage in a network, in a TT network. Now, I'm trying to explain it for a non-electrical engineer, because more than sometime our webinars we have engineers other than electrical engineers from the fire department and other places. So safety engineers are also there. I'm trying to explain it for a layman language. Now, here on the picture, what you are seeing is earth. It's soil, or our mother earth. It's infinite. We call us infinite earth because endless. And this is, we always say, it's of zero potential. Of course, it has to be of nil potential. We have an infinite earth. Now, our electrical installation need to have a contact or a connection with this infinite earth. For this purpose, we put an earth electrode in soil because we are in a TT network. So the current has to go back to the source through the earth electrode, through the soil, returning back through the earth electrode of the neutral of the transformer. As a result, your protective device is going to trip. Now, this, in order to create a connection with this infinite earth, which is at zero potential, we put an earth electrode in soil because the earth has got a certain resistivity. It is not zero. It has got certain resistivity depending upon the soil, probably from sometime 10 ohm to sometime several thousands. Now, Any joint will create a contact resistance. You know very well. Even if you terminate two wires, and if there is a resistance, of course there will be a contact resistance always. Whenever you make a joint, of course there will be a contact resistance. In case of this contact, that means the contact from a wire to the earth, it is over an area. Over an area means in a normal contact, you can see the contact and the resistance is between this or within this particular contact area. Whereas in case of an earth, this resistance is over an area. A resistance area, for example, the definition for an earth electrode only. You should always read in this way: earth resistance area for an earth electrode only, the surface area of ground around the earth electrode on which a significant voltage gradient may exist. What you can do is, I will show you how this is written in the standards IS 3043 and IS 732. I'm sure you are able to see the screen. I'm showing you NEC, National Electrical Code. Okay, before that, I'm showing you the IS 3043. All of you know very well the code of practice of earthing. I am searching for the word resistance area. So on the definition, you can see resistance area. Resistance area, the surface of ground on which a significant voltage gradient may exist. You can also find the further explanations in IS 3043. I am skipping through some of the explanations. Similarly, in NEC, National Electrical Code of India, here also the 2011 version, you can find the resistance area. Now you see here the resistance area, voltage gradient. The earth electrode should not be installed in proximity to a metal fence, and all these requirements are there. Electrode resistance area. Once when we talk about earth electrode, we should have a clear understanding about the resistance area. Otherwise, we will end up with trouble. Coming back. So, resistance area is already very well established and explained in the respective standards. You have to refer that. What does this mean is, actually this resistance is applied over an area in the soil. For example, here item number 1 is an earth electrode, 2 is the mother soil, and this circle or this hemisphere is the area which is influencing the resistance of the earth electrode, and you can say that this is the area of the electrode, influencing area. Now, this influencing area, it depends on the soil. Maybe in one place it is 7 meter, and maybe in another place it is 30 meter, and in another place it will be something else. We have no control over this influencing area. So I am just putting this influencing area as a resistor, for example, and on the other side you have the infinite earth, and point number 1 is the tip or the terminal of your earth electrode. So between the earth electrode terminal and the mother earth, you have a resistance, and whenever there is a current flow through this particular earth electrode, a voltage is created. Very simple to understand. Because there is a resistance and there is a current flow, a voltage is created, and the important part is this voltage will be over this particular area. That means here you have the point number 1, which is the terminal of the earth electrode, and one moment. Okay, I got a message from somebody who says that I showed the 2 times the definition, and the definitions were not shown. If you have any doubts, probably after the presentation, I will show you both these slides. I'm sorry if it was skipped. Now, this resistance is over this particular area. between point number 1 and 2. Earth electrode in contact with soil and the applicable area of the voltage gradient. I am trying to explain you the earth electrode because it's a very influencing factor and it's a confusing factor. My idea is to explain you the influence of this factor with the protective measure, automatic disconnection of supply. Now, there are three factors which is influencing this particular electrode resistance. The first one is the resistance of the metal electrode itself. The second one is the joint, the contact resistance between the electrode and the mother soil. And the third one is the resistance of the soil itself. So the resistance of the soil is the most influencing factor. The first two are not much influencing, whereas the resistance of the soil is the most influencing factor in this particular case. Now, I'm showing you a table from IEEE 142. I don't remember the table number. You can find this IEEE table. In this particular table, they are trying to explain, or they are trying to define, or they are trying to find out the influencing area as a hemisphere. Let's say, for example, this is the hemisphere and the distance from point number 1 to point number 2. And then they try to measure the resistance, the applicable resistance of that particular electrode. Now, in this case, in this table, 100% resistance of the earth electrode is achieved at a distance, or the influencing area is 7.6 meters. 52% of the influencing area is within 15 centimeters. That means from the earth electrode within 15 centimeter, half feet, 52% of the voltage gradient has reduced. Within 30 centimeters, the voltage gradient, the voltage has reduced to 68%, and for example, 7.6 meters, about 100% of the resistance is achieved. How we can read it in this cases? Further explanations are there in the IEEE 142. So it is like this. You have a series parallel combination of earth, and I don't want to explain this much because this is very well explained in the IEEE 142. You can download it at free of cost. Of course, it is chargeable, but somebody had uploaded in the internet. So the total resistance RE is a sum of several series parallel combination of resistors. This is just to analyze what exactly is going to happen. And the voltage gradient is across these 2 points. Here on the right side, you can see the voltage gradient. Voltage gradient means between point number 1 and 2, there is a voltage exist during the fault. Remember, this voltage gradient or this potential difference to a remote location in the gradient is the operating voltage of the system. The fault voltage, the maximum, the peak of this voltage is the maximum operating voltage of the system. Let's say your fault is 230 volt, then the peak of the gradient is 230. I always try to repeat this particular word in several of my presentation because in India, we have a misunderstanding. You can find this misunderstanding in several tenders. Let's say, for example, including some of the metro railway earthing tenders, they say 230 volt application, 50 kiloampere fault current going to earth, and they design an earth electrode, a large mesh, thinking that a large voltage, 15 kV voltage gradient or 15 kV step potential is going to come. That is not correct. The peak of the voltage is the operating voltage. Now, I tried to put the same calculation of IEEE 142 for various operating voltages. Say, for example, in a line-to-line 400 volt system, that means in a normal condition, one of the phases creating a fault, the peak of the voltage, fault voltage is 230 volt, means in case of a fault of negligible impedance, the exposed conductive part is having a potential of 230 volt. So within a distance of 0 to 15 centimeter, within half feet, the 50% of the voltage has dropped. So that means if you measure the potential from the earth electrode to the next 15 centimeters, you can measure half of the potential. This is for that particular soil. Probably in another soil, it varies. So IEEE didn't explain for which soil resistivity this is made, or probably I didn't read that particular clause. For example, the second case, within 30 centimeter, approximately certain amount of voltage is, say for example, in the graph I have explained, 50% of the voltage is dropped. Then 16% is dropped within 30 centimeters additionally, 15 centimeter to 30 centimeter, about 16% of the voltage is dropped. And at a remote place, 7.6 meters, the entire applied voltage is made. Now, what you should understand is there is a parameter called step potential. For a 230 volt or up to certain voltage, this is not very critical. Now, a person who is standing at a distance away from this particular earth electrode, he can have step potential. But anyway, I'm not explaining it much because that is related to earth electrode. Our today's subject is automatic disconnection of the fault. What you should also understand is, in case of a fault, this voltage gradient will be created at two places. One is at the place where the fault is happening, and the second one is the place where the fault is returning back to the source. Two earth electrodes are there. As a result, both the places voltage gradient will be created. Another misinterruption. Anyhow, this is also not a part of our presentation, but still for the explanation, because a lot of time people always ask about chemical earth and its applicability. Now, we have made a webinar, I think about 4 or 5 months back. You can go to the our link and you can look at the video. So where these are very well explained. So just for your information, if you have one earth electrode in soil, let's say a 2 centimeter, 20 millimeter earth electrode in soil, there is a study paper, not one study paper, several study papers, where this entire system is explained. Let's say, for example, a 2 centimeter, 20 millimeter electrode is offering a resistance of 635 ohms in a typical environment. For a typical length. If you put a 50 centimeter backfill, that means almost half meter of backfill all around this particular electrode, or instead of 2 centimeters, 20 millimeter earth electrode, if you put a 50 centimeter or 500 mm, means half meter earth electrode, or if you put a cage of half meter in this way, the earth electrode resistance will be reduced from 635 ohm to 351 ohm, about 45% reduction. But please note that the size of the backfill compound is 50 centimeters, almost a half meter all around. And the pipe, if you are using, it is 50 centimeter, or the cage is 50 centimeters. So these are large electrodes. You can find the relation of increasing the diameter of the electrode and its relation to the earth resistance in IS 3043. The same principle applies here. Now, what I wanted to clear to you is, instead of backfill compound, the same result is achieved by increasing the diameter of the earth electrode. If you use this chemical or this backfill compound, what happens is this backfill compound will have a lower resistance. As a result, it corrode the earth electrode much faster. So be very careful. The standard IEC recommends backfill compound for application where the soil resistivity is higher than 3000 ohm meter. Even the Indian standard recommends backfill compound or any chemical for soil resistivity more than 3000 ohm meter. If you are in a place with a lot of moist or wet soil and the soil resistivity is only 100 ohm meter or 200 ohm meter, don't put a backfill compound, because it will corrode your electrode much faster. Getting 1 ohm or 0.5 ohm is not important at the moment. So a 100 mm backfill compound, which is generally used in the industry called as chemical earth, it can influence 3 to 5% or 3 to 10% of the total resistance. So now coming back to our subject, automatic disconnection. One of the network which we use is a TT, where the fault current is going to flow through the earth electrode. And you have to be clear that this earth electrode is having certain resistance. And in this particular loop, there are two resistances added by two of these earth electrodes. Let's say, for example, in an ideal situation, each of these earth electrode is 1 ohm. Now, with these two earth electrodes, we are actually adding 2 ohm in this particular loop. So 2 ohm is additionally added in this particular loop. As a result, current will be much lower. Once when the current is much lower, the protective device OCPD will not create an automatic disconnection, or that particular device is not efficient. So in an ideal situation, a 230 volt fault can produce a maximum of, let's say, 230 volt divided by 2 ohms, about 115 amps in an ideal situation. But ideal situation will never happen. In a general situation, the fault current will be much lower. It may be sometimes 10 amps, 20 amps, something like that, very, very less. It can, in a TT network, fault current can be never be higher. Also, please note that fault means something which is happening to earth. Between line to line or between line to neutral, what is happening is a short circuit. So you should understand the difference between short circuit and a fault. What we are talking is a fault. In a general situation, in a 230 volt TT network, fault current will be much lesser. Number two, in low voltage, in a lot of places, as I said, metro railways, most of the metro railways across India, for signaling application for an UPS neutral or UPS body or some of the SNT equipment, they make a large grid, assuming that 50 kiloampere fault current goes to earth. I really don't know who gave this idea to them. But as a result, the whole safety is violated in that particular case. Now, for your information, TT network, assuming 25 or 50 kiloampere fault current is wrong. Several times people think that large fault current is going to flow. The network is TT and low voltage. This is absolutely wrong. Ideally, only few amps is possible because you have 1 plus 1 ohm, 2 ohm, or much more resistance in this particular loop. Number two, in a TN network, higher fault current is possible. Of course, 10 kiloampere, 25 kiloampere, 50 kiloampere may be possible. But you should understand that that particular fault current is flowing through a metallic conductor. It is not going to flow through the earth electrode in soil. Of course, the amount of current which is going to flow through the earth electrode may be very, very less, a few milliamps or very less. Majority of the current flows through the metallic conductor. So in a TN network, the size of the metallic conductor fault return path has to be larger enough so that that particular conductor is not damaged and it is not creating any fire accident. So, in conclusion of this slide, earth electrode for carrying high fault current, say for example 50 kiloampere, is never required for a low voltage application. Not even for low voltage, even for a high voltage application, this is never going to happen. Why I made this statement is nowadays, if we look at the specification of the electrical requirement, most of the time, chemical earth electrode with 50 kiloampere fault current is requested by the industry for application in low voltage. This is never going to happen. Please note that you don't need it. So for automatic disconnection of fault protection, IS 3043 has explained the subject in clause number 23.1, basic purpose of earth fault protection. Please read it very carefully. The earth fault loop impedance has to be low enough to allow adequate earth fault current to flow to cause an overcurrent protective device, for example, fuse or a circuit breaker in the faulty circuit to operate in a sufficiently short time. Or if this is not happening, then where it is not possible to achieve a low enough earth fault loop impedance, disconnection may be initiated by fitting a residual current device RCD of 30 milliampere rating as specified in IS 732. So this particular clause explains very clearly that you have two options. One is your MCB should trip, but you have to have enough current to operate that particular MCB. In order to have enough current to operate that MCB, you have to have a very low earth fault loop impedance. And if this is not possible, you have to go to the second option. You install a 30 milliampere RCCB. This is the correct way of reading. And please note that similar wordings are also included in the upcoming regulation, CEA Central Electricity Authority measures relating to safety and electric supply. So you have to be careful in future. Now, with respect to fault protection by automatic disconnection of supply, there are two tests required. The first test is a fault loop impedance test. With a fault loop impedance meter, you have to measure the impedance of the circuit. You have to establish the fault current, then compare the fault current with the disconnection time of your protective device. So you have to have a meter, you measure the current, or you measure the fault loop impedance, you measure the fault current or calculate the fault current, then you compare it with your protective device and see that it is able to disconnect within the time specified. Number two, RCD test. RCDs generally have a button, test button on the RCD. The RCD test is not about pressing the button and finding out your RCD is working. That is not there. RCD test is carried out with an RCD tester. So there is an RCD tester and you have to connect the RCD tester at the output of your RCD, and this device will inject a current and it will find out the tripping time of your RCD. So both these tests are depending upon your application. One of these tests may be required. And you also should understand that for fault loop impedance test, you require a proper fault return path, metallic fault return path. So if the metallic fault return path is not there, then the first test will not work out. You have to always use a 30 milliampere RCD, and with the 30 milliampere RCD, you cannot operate your circuit, operate your industry, or run your industry, run your hospital, because it will sometimes create noise and stripping. Also, please note that this test, protection by automatic disconnection of supply, is a test which is among 18 inspection points and 10 tests. This test is one among the 18 inspection plus 10 test. That means 18 plus 10 out of 28. This test is one of them in a low voltage installation. Please note that carrying out this test alone cannot ensure safety. Only by doing fault loop impedance, thinking that only by doing fault loop impedance or RCD test and thinking that the circuit is safe is not correct. So this is one among the 28 requirements. Please keep this in mind. So at CAPE, we have a very good technical team. We can help you in understanding not only this test, all the tests, and we can also provide and supervise improvement plan. See, the purpose of carrying verification is to find out the mistakes in the electrical installation. So finding out the mistakes in the installation is not going to help you. You have to implement the improvement plan. So we can not only make educate you how to test and what kind of test, and we can also make an improvement plan to you, and we can supervise that particular improvement plan. This is the service which we are offering for the last few years. So with this, I would like to stop the presentation. Please note that the protective measure which we discussed today is not only I will just go back to the slide. The protective measure which we discussed today is efficiency of automatic disconnection of supply. It is not only automatic disconnection of supply, it is the effectiveness of automatic disconnection of supply. That means it has to have certain time and certain other things are also there. With this, I would like to stop the presentation. Thank you very much.
Sir, the slides, you're unsharing the slide
Yeah,
or?
no. I have just shared the Electropedia. Somebody told that the slide was not visible. It is not a slide. I am just on the internet.
Okay.
In the web page, Electropedia, this is the online vocabulary of IEC. You can,
Okay.
the customers also, the participants also can search these wordings in the, for example, in the online browsing platform of ISO. So I just explained the verification. I'm searching verification. Oh, sorry, there was a spelling mistake. Verification. If you search, then you will get the answer. I'm sure this time it is visible. Verification, confirmation through the provision of objective evidence that specific requirements have been fulfilled. So this is how you should do. Also, I shared one more point, which is the effective area. I'm sharing the PDF file IS3043. I don't know whether it is visible. Mr. Dominic, hope this is visible.
Yes, we can.
Yeah, IS standard. I am just referring to the resistance area, the definition resistance area, the surface area around the ground on which a significant voltage gradient may exist. You can also refer to the same standard about the explanations of resistance area. You can also go to the National Electrical Code of India 2011. Here also a lot of explanations are given. So these two were, I think, missed. Thank you very much. I hope this was clear.